All right, so this is what you're going to see. This is the periodic table. If you don't have one of these, print one of these out. You need to be able to reference one of these all the time, okay? Again, there's one in Canvas in the Getting Started materials. If you need to get one, some of you may have one already, but if you don't, snag one, okay? So we see a few different things here. If we look at that, the one that's exploded there out, the beryllium, we can see a few different things. We see at the top of it the atomic number. That's the number of protons that are in that particular atom. We see the chemical symbol. That's the shorthand way that we're going to reference that atom all the time, okay? We are very, very rarely going to write beryllium down, but we'll use Be, okay? The next thing there is the atomic mass, and we'll define what that means in a little bit later, okay? But effectively, it is how much that atom weighs on average, okay? We talk about isotopes, so we can talk about that for a second, okay? The uranium that we just looked at, we said there was two different types, right? Uranium-235, uranium-238. They got different masses. One weighs 235, one weighs 238. If I go dig them up somewhere in the soil, some percentage that I pick up out of the soil is going to be 235. Some percentage I pick up is going to be 238. Do you agree with that? So what we do is we do a weighted average of those isotopes, and that's how we come up with that number. So if we look down here at number 92, at uranium, well, for example, this one doesn't have the precision that I need. But let's look at carbon. There's carbon-12. We saw that a minute ago. There's also carbon-14. That's the carbon used in radiocarbon dating, if you've ever heard of that before. If you're a biology person, maybe you talked about it. Anthropology would have talked about it. Archaeology would talk about it. There's two different types, carbon-12, carbon-14. Carbon-12 is way, way, way more prevalent than carbon-14. So when we take an average, if we pick up a handful of carbon, on average it's going to weigh 12.01 because most of it's going to be 12. Very, very little of it's going to be carbon-14. That's where those numbers come from, okay? But again, what that number means is if I pick up some of it, that's how much it's going to weigh on average, okay? Again, not going to ask you to take a test on memorization of this stuff, but it is very much in your favor to know these things because we're going to reference all these chemicals by their symbols, okay? And so we need a working knowledge when I say CH3 that we know that's going to be a carbon and 3 hydrogens, right? Question here. I'm going to let you go back and look. So I'm going to flip it back to the previous slide before I turn on the question here. How many protons are in a silver atom? So we'll go back and take a look at our periodic table. These names are kind of weird, right? Some of them make sense. Some of the symbols don't make sense at all, like why is potassium K, right? But it turns out, and why is sodium Na? It turns out that a lot of the things are named for their Greek or Latin names, right? So lead, Pb, is actually plumbum. Fe for iron is ferrium. I mean, they're named for their Greek and Latin names, and those symbols kind of transcended history, right? This guy, Mendeleev, he just observed all the known elements at his time, right, which was a while ago, and he started laying them out in order, and he just created a table. And anytime he just increasing mass. So here's the first thing I know. Here's the next thing I know. Here's the next thing I know, and just laid them out in order of increasing mass. And then anytime he came across two chemicals that had the same kind of properties, he would put them in a column with each other, right? So it was like, hey, this thing, when I put it in water, it explodes. This thing also, when I put it in water, it explodes. So I'm going to put them in the same column, right? And that is the basis of our periodic table, right? This guy is credited with creating the periodic table, and his looked something like this when he started, right? We knew far fewer elements than we know now. What he learned from this is that you can group these things based on properties. So everything in this group, in this column here, has similar properties. Everything in this column has similar properties. Everything over here in the last column has similar properties. And we didn't really know why at first, but it was a pretty cool thing that he found out, right? And so again, this gave us the basis of our periodic table. So this gives me a second to kind of soapbox here. When you see something called a scientific law, all right, so law of gravity or periodic law. Laws are made by taking observations, taking data, and then talking about what you saw in the data, right? I drop this thing, it falls. It falls at some increasing rate. That's gravity, right? Periodic law. When I lay these things out, I get these nice periodic patterns that repeat. That's different than a scientific theory. A scientific theory, even though it has the word theory in it, is usually more complete than a law, because a theory has the background, the how it works in it, right? Laws don't do that. Laws just say, we saw this and it happened and it works. Theories say, this is how it works, okay? So a lot of the misconception in popular day stuff is, oh, it's only a theory, so why should I believe it? Theories are generally more rational than laws, okay? They do a better job of explaining than laws do, okay? So right now, we're taking this to be law. It was just observed, and that's what it is. In chapter 9, we'll talk about the why. We'll talk about the theory behind how it works. All right, so now we've got a modern day periodic table here, and we want to talk about how we can classify stuff on this periodic table. And one of the easiest ways, one of the broadest classifications, is we can classify things as either being metals or not, okay? So the stuff that you see in that kind of beige gray color up there, these are metals. Metals show up on the left-hand side of the periodic table and toward the bottom of the periodic table. What do you guys know about metals? What did you learn in like middle school, high school about metals? How can we tell if something is a metal or not? Yeah, if it conducts electricity, that's a great way to see if it's a metal, right? Typically, shininess is a reasonable indicator of a metal. Does it conduct heat well? Does it conduct electricity well? Is it malleable? Does anybody know what that means? Yeah, can you squish it, right? Can I hammer it into a thin sheet? How about ductile? Can I draw it into a wire? Can I pull it into a wire, right? Is it shiny? Does it conduct electricity or heat? Is it malleable? Is it ductile? Another thing we'll learn is that metals typically give away electrons, right? We might not know that yet, but if we put them in a chemical reaction, metals typically like to give away electrons. What about nonmetals? Well, they're all the other things, right? They're not good conductors of heat and electricity. They're typically brittle. They don't hammer into thin sheets or draw into a wire, they break. Metals are typically solids, right? I know of mercury that is a liquid metal, and I know of gallium that if I hold it in my hand, it will melt by the temperature, by the heat of my hand and become a liquid metal. Most of the rest of them are solids, right? What about nonmetals? Well, nonmetals are the ones that you see in green, right? They're the ones on the right-hand side toward the top of the periodic table, and they're kind of everything. Let's look at column 7A or column 17 over there. We call that column the halogens. Fluorine and chlorine, so F and Cl, those are both gases, right? Bromine is a liquid, and iodine is a solid. So we kind of run all states of matter in nonmetals, okay? Nitrogen and oxygen are gases, carbon's a solid. Everything in group 18 or group 8A, those are gases, okay? And we'll talk about those a little bit later. But so we're pretty varied in our nonmetals. But in general, they're bad conductors of both heat and electricity. And when they undergo chemical reactions, they take electrons, right? They will steal electrons, typically from those metals that like to give them away. So the air you breathe is a great example of a nonmetal. Like we said, metals, left-hand side of the periodic table, good conductors. They're malleable, they're ductile, they're shiny, and they usually give up electrons when they undergo chemical reactions. We haven't talked about chemical reactions yet, and that's okay. All right, so then we got this thing in the middle. If we go back and look at our periodic table for just a second, we got that purple stuff in the middle there, and those are called metalloids, or semi-metals maybe sometimes. Or have you ever heard the term semiconductor? So these things are somewhere in between a metal and a non-metal, right? They got properties that are kind of in between. So where do you know semiconductors from? It's probably the most important discovery in your existence, right? In the last 100 years, for sure. In your phone, absolutely, right? The chip that's in your phone that makes your phone go is made probably of silicon. I don't think we've got fancy gallium arsenide ones on the market yet. So metals conduct electricity easily, right? Non-metals don't. Metalloids or semi-metals can be switched on and off to conduct electricity. We can apply a little bit of current to it or a little bit of voltage to it, and we can cause it to conduct electricity when we want it to and when we don't. That allows us to establish things like digital logic and turn on and off currents. That lets us make ones and zeros. That lets us make binary. And that lets us do computer programming and all that kind of good stuff, right? So we need these semiconductors to make all electronics go. Or at least all small electronics go, okay? So one of the most important things in mine or your lifetime. So silicon is the most common. It is a natural semiconductor. We can dig it up out of the ground and do a little refining on it, and it's ready to go. There's also a few others, and we can make compounds out of these things, like we can take gallium and arsenic and make gallium arsenide, and make a few different types of semiconductors, right? But the important thing to remember is that they have properties that are in between metals and nonmetals, and we exploit that in-betweenness to make digital devices out of it. All right, so another broad classification on the periodic table is the difference between what we call main group elements and transition elements. Main group elements are the ones that are in the tall columns on the periodic table, and we see those on either side of the periodic table, all right? We will spend a lot of time talking about main group elements in Gen Chem because main group elements are easier to talk about. They make nice stable charges, and their properties are nice and neat. The properties of transition elements get a little bit messy, and so we try to stay away from them in Gen Chem. That doesn't mean we'll never talk about them, but where you really learn transition metal chemistry is in inorganic chemistry, which is Chem 411, okay? So we will spend most of our time talking about the yellow stuff. We will spend a little time talking about the blue stuff. So let's see if we can, and this is not a clicker question or anything, let's see if we can sort out what these are. Are they metals, nonmetals, or metalloids? So that first one up there, Ba, that's barium. Find barium on a periodic table and tell me, is it a metal, nonmetal, or metalloid? Where is it located on the periodic table? What's its atomic number? Let's go with that first. Say again, 56. What column is it in? Column 2. So that's on the left-hand side of the periodic table. So is this thing a metal, a nonmetal, or a metalloid? Metal, for sure. How about B? B is that is iodine. I is iodine. Where is it on the periodic table? 7th column, column 7A, or column 17, depending on how which periodic table you're looking at. So is that going to be metal or nonmetal? How do you know? It's on the right-hand side. That's right. All right, how about, that's oxygen. Atomic number 8 in the column that is, 2 columns from the right-hand side? 3rd column from the right, I guess is the way I should say that. You agree with that? Metal, non-metal, or metalloid? Non-metal. D, that's tellurium. That one's harder. You have to figure out exactly where that stair step is for those metalloids, but that one is a metalloid, right? Okay, so we did the broad classifications. We said metals, nonmetals, metalloids. Then we said main group elements versus transition elements. Now we're going to look a little more in detail, and each group actually has a name. I should make that clear, all right? So groups are columns. When I say group, I mean the column. If I say period, I mean row, okay? So groups are columns, periods are rows. And each group, so each column, has a name. And they all have similar properties. So group 1 over there, group 1A, they're called the alkali metals. And their most important property or biggest property is that they react violently with water. If I were to put those things in water, they would cause explosions, okay? Group 2 are alkali earth metals, and they also react with water, but not quite as violently as the group 1 metals, okay? All the way over on the far right-hand side of the periodic table, those are called the noble gases, and they are, by and large, inert. They don't do anything. They don't react with anything. If we try really, really hard, we can make them react, some of them, but left in their natural state, they're not going to react. Group 7A are called the halogens. You've probably heard that word before, right? Halogen. Where does that word come from? Or where have you seen it before? In a chemistry class before? Where in real life have we seen it? Anybody ever had to buy a headlight for their car? They're halogen bulbs. They're filled with these types of gases, and those gases will emit a light when you pass a current through them, okay? Have you ever seen a neon sign before? Like a beer sign, right? Those have the noble gases in them, right? Either neon or argon or one of those things, and they shine a particular color. Group 6 here, the oxygen group, that has a name too. It's called the chalcogens. Very few people actually write that one down. But all of them have a name. No one remembers what any of these other ones are called though, okay? 2 of the periods have names down there too. We have the lanthanides at the very bottom and the actinides at the very bottom. I want you to take a look at the numbers on those at the bottom and pay attention to the fact that those are actually cut out of the middle of the periodic table, right? So from 58 to 71 goes in that little crack in between right there, right? So the periodic table should be a lot wider than it really is, but we always cut those pieces out and put them down below for reasons that we'll explain when we talk about electron configurations. So you can click on this later and watch it if you want to. This is people throwing chunks of sodium into a pond and making explosions happen, okay? So again, the group 2 stuff, the alkali earth metals, they will react with water, not as strongly as the group 1. They will burn. So you can burn magnesium. You might have done that in a lab in high school maybe or something like that. It burns very, very, very brightly, bright white light, right? The halogens are neat for reasons that we can't really 100% get into in Gen Chem 1, but you'll learn about in Gen Chem 2. So something like iodine, for example, is a solid, but it's held together by a type of forces that are pretty weak called intermolecular forces. And so if we heat it up a little bit, we can turn it directly from a solid into a gas. It doesn't go through the liquid state. We call that sublimation. And so this is a neat thing you can do. You can take some iodine, you can heat it up on a hot plate, and you'll make a nice purple gas inside of your container because it's turning into iodine gas. And then if you have some cold water or some ice or something on top up there, you can grow little iodine stalactites off of the thing that you've got on the top up there, right? Noble gases, we've seen them before. Helium goes in balloons. Neon, argon, krypton go into making neon signs. We call them neon signs, but they're noble gas signs, right?